This video, with a total duration of 2 hours and 38 minutes, took 1 month to produce. If you like it, consider subscribing first so you won't lose it later. The video starts with a universe full of mysteries, where rogue planets wander aimlessly, and Jupiter's fiery core hints at secrets of nuclear fusion. It explores the possibility of life and how the warming of our planet might intersect with China's secret Mars mission, potentially providing answers for our future survival. Today, join me as we unravel these mysteries one by one.
What you're seeing now is the Martian South Pole ice cap. Beneath this layer of ice lies a massive lake of liquid water. It spans about 20 kilometers in diameter. On July 25, 2018, NASA published an article titled, "Large Underground Lake of Liquid Water Discovered Deep Beneath the Surface of Mars." It provided further evidence that liquid water once existed on Mars, and the findings were published in the prestigious journal Science. Scientists believe that around 3 to 4 billion years ago, the surface of Mars held large amounts of liquid water. This water shaped Mars terrain, leaving behind traces that remain clearly visible today. So how was liquid water on Mars discovered, and how did Mars transform from an ocean world into the cold, barren desert it is today? Today, let's talk about what exactly happened on Mars that caused it to become what it is now. Since the beginning of space exploration, Mars has been a prime target for scientists. The goal of exploring Mars is clear: to determine whether liquid water once existed there and whether life ever emerged. Since 1960, humans have launched 50 missions to Mars to confirm the presence of ancient liquid water. Scientists have studied the planet's terrain, rocks, and minerals in detail. They've proven that not only did Mars once have abundant liquid water, but even today, liquid water activity still exists on Mars. In 2015, NASA confirmed evidence of liquid water flowing on modern-day Mars. It was a surprise to discover liquid water on a planet 100 times drier than Earth's deserts. If ancient Martian water gave rise to life, we might one day find fossils on Mars, or at least evidence of microbial existence. That's why the Curiosity and Perseverance rovers are tirelessly searching for new clues. If they truly find something, it would confirm that, as long as liquid water and relatively mild conditions are present, life has the potential to emerge, and that would also mean life might be widespread throughout the Milky Way, perhaps even across the universe. But if Mars had liquid water and still didn't develop life, it would suggest that a crucial ingredient is missing to uncover what Mars was like in the past. Scientists deployed the Curiosity rover to explore Gale Crater. By examining the remains of ancient Martian oases, we can more accurately understand the planet's history. Was Mars once a blue planet, or has it always been a barren desert? Did life ever appear on Mars at all? The answers to these questions lie with the data sent back by these rovers, ultimately through data returned by Curiosity, Zhurong, and other missions. We now know that Mars not only once had liquid water, it may have once been a beautiful blue planet, just like Earth is today. In fact, there is abundant evidence of liquid water on Mars. First, the geological evidence. Mars' surface contains many dried-up riverbeds, alluvial plains, and lake sediment deposits. These features closely resemble water-eroded landforms on Earth. Their existence suggests that large quantities of liquid water once flowed on Mars, sculpting its present-day terrain. Second, the mineralogical evidence also supports the presence of ancient water. The Curiosity over discovered hematite, sulfates, and carbonates, minerals that require water-based chemical reactions to form. It also found smooth, rounded rocks on the Martian surface, rocks that had clearly been worn down by flowing water. Meanwhile, China's Zhurong rover discovered coastal sedimentary structures 10 to 35 meters beneath the Martian surface. These structures further confirm the presence of past water, possibly even oceans. So if Mars once had so much liquid water, why did it all disappear? To find out, scientists conducted in-depth research into Mars' climate, geology, and atmosphere. They proposed a theory about how liquid water vanished over time. They believe that, around 4 billion years ago, Mars had a thick atmosphere and a warm climate, similar to Earth today. Rivers, lakes, and seas existed under these mild conditions, and liquid water was stable on the surface. But by around 3.5 billion years ago, Mars' core began to cool. Volcanic activity weakened, disrupting the carbon cycle. As Mars' magnetic field weakened, solar winds started stripping away the atmosphere, blasting it into space. Carbon dioxide became trapped in carbonate minerals, causing the climate to cool. Liquid water could no longer remain stable on the surface. After hundreds of millions of years, Mars' atmosphere had thinned drastically to only about 1% the density of Earth's atmosphere. This led to a cold and dry climate. Liquid water gradually disappeared from the surface, retreating underground or to the polar regions. This real image of Mars' atmosphere, taken by an orbiter, shows just how thin it really is. By around 3 billion years ago, Mars entered its late stage. Water continued to decline, and the surface turned into a desert. Mars' climate became increasingly hostile. The thin atmosphere couldn't retain heat, leading to surface temperatures as low as -63 degrees Celsius. Liquid water could no longer survive on the surface, existing only as underground ice or polar ice caps. So here's the big question: did Mars ever harbor life? Some scientists believe that Mars' early mid-latitude regions might have contained oases that lasted from thousands to millions of years. These oases could have served as habitats for life, offering key clues in our search. If these Martian oases really existed and persisted long enough, they may have provided a crucial window for life to emerge and evolve. This would be of great importance to the study of Martian life. Unfortunately, we haven't yet found direct evidence of past life on Mars. However, Italian scientists, using radar from the Mars Express spacecraft, discovered a liquid water lake 20 kilometers wide beneath the South Polar ice cap. Additionally, analysis of seismic data from the InSight lander suggests that a layer of liquid water may exist 10 to 20 kilometers below the surface. These underground water reservoirs might be critical habitats for Martian life and represent key targets for future exploration. As we all know, water is essential for life. It is one of the key conditions for life to exist, and Mars, a potential second home for humanity, has limited but crucial water resources. These will be vital for future exploration and colonization. For now, we can confirm that subsurface water and polar ice caps on Mars can serve as future water sources for human bases. These water sources could provide drinking water, be used to produce fuel and oxygen, and most importantly, support agriculture and industrial activities, making long-term survival on Mars possible. To further uncover Mars' history and signs of life, the Perseverance rover has already completed most of its sample collection mission. It aims to return samples from Mars by around the year 2030. When that happens, the rocks and soil collected from Mars could help us accurately understand its past and finally answer the question, did life ever exist on Mars? Let's hope that day comes soon, sooner than we think.
Why do you say? The future of humanity is either ascending or silent. This is called the Great Filter Theory. We, now on the threshold of impacting a first-class civilization, once you fall, may be trapped in a level 0.7 dark forest forever. But if humans can actually graduate from kindergarten and skip the level, what would that look like? And the rule of customs clearance has only one energy. This is the Kardashev scale, the ultimate rank of cosmic civilization. Let's start with the first episode. Unlock the power of creation step by step. In the Kardashev hierarchy, the first level of civilization, a society, has fully mastered the full power of its parent star. This means that it can handle, store, and use all available energy on the planet: solar, wind, geothermal, tidal. It can even control the energy of storms, earthquakes, and volcanoes. From a numerical perspective, energy consumption of a first-level civilization, that's about 10 to the 16th watt. As a reference, the current level of human civilization is roughly 0.7, although we have not yet reached, but it's getting closer. The allure of lower civilizations is its highly developed and interconnected society. Imagine that. Cities are powered entirely by clean energy. Fusion reactors provide a steady stream of and pollution-free electricity. Global weather control, likely to become a reality. Regulated through advanced technology. The rain has ended the drought, or weakened the hurricane before it makes landfall. By stabilizing the pressure of the tectonic plates, the threat of earthquakes may be neutralized. Giant orbiting mirror. You can adjust the intensity of sunlight in a specific area. Nature will no longer be a passive force to bear. They are objects that can be actively managed and regulated. Unique to first-level civilizations, one of the most exciting technologies. It's a planetary energy grid. This network, not only does it connect countries, connecting continents and oceans, will come from the desert. Energy from solar farms or deep-sea wave generators. Stable delivery to all parts of the world. Another wonder is climate engineering. We will be able to actively fine-tune the Earth's atmosphere to balance global temperatures, reduce extreme weather. You can think of it as a global thermostat, ensuring the stability and habitability of the entire planet. Living in a first-level civilization, it's like stepping into a science fiction novel. Humans and machines will seamlessly merge. Smart cities are built from scratch. Coordinated traffic, energy distribution, communications by artificial intelligence. Even healthcare. Public transportation will be clean and high speed, probably based on maglev or hyperloop barrels. You can cross the globe in a few hours. At that time, there will no longer be a distinction between developed and developing countries. There's only one, highly interconnected energy and equal rights. Unity, civilization, culture, and communication will also undergo a revolution. Real-time translation technology pervades the global language. Ubiquitous internet, blurring the concept of national boundaries. Humans may develop a sense of collective planetary identity, no longer based on countries, but united as a community on Earth. Education can almost be completed by homeopathy, perhaps through direct neural connections, or an immersive virtual environment to achieve. Driven by abundant energy and collaborative tools, anyone, anywhere, can unleash creativity and innovation. Will prosper like never before. But to reach the first level of civilization, technology alone is not enough. Collaboration is essential. A civilization must overcome deep politics, cultural and environmental differences, to unify its energy use and infrastructure, and avoid self-destruction due to war or ecological collapse. Despite this, the payoff is enormous. The first level of civilization is likely to be approaching. Become an interplanetary species, with vast resources and global coordination capabilities. We can start terraforming nearby planets, transform or build large space habitats, space elevators, orbiting solar power stations, and asteroids. Mining could become a part of everyday life. Earth will be just a starting point, a home port for species ready to explore the universe. Second-level civilization. It has gone far beyond the limits of the planet, capable of harnessing the full energy output of its parent star. If you say, a first-level civilization controls the energy of a planet, then the second-level civilization harness the full power of its star. It's about 10 to the 28th watt. It's an incredible leap in capability. Marks the scale of a species. Reach stellar level. Related to this level, the most iconic concept is the Dyson sphere, a wrapping star, to capture its full energy output. Although a complete sphere may be impractical, but by millions, an orbiting solar collector, Dyson cloud, they get the job done. The technology of a second-level civilization is not only more powerful, but into a completely different dimension. Entire planets can be transformed, or designed as a facility with a specific function, such as industrial production sites or data storage centers. This civilization may be able to move planets, altering the asteroid's orbit, or use attractive force control technology to adjust the operation of celestial bodies. The interconversion of matter and energy will become possible, allows for the creation of anything at the basic atomic level. Even black hole engineering could start at this stage. Use it as an energy source or conduct cutting-edge physics experiments. This civilization is more than just surviving. It will shape the stellar world and even space-time itself. Living in a second-level civilization, it feels like becoming, for a galactic superorganism, the scale of society for us today, almost incomprehensible. People may live in an orbiting star. Each of these megastructures could accommodate billions of people. It may also live among the planets, floating artificial habitat, or hollowed-out asteroids. Internal energy is almost limitless. Scarcity has become a historical concept. Need a new city to print directly. I want to travel through the entire solar system, through near-light transportation systems or space-folding technology. It only takes a few minutes or hours. Daily life will be defined by post-scarcity abundance. Food, water, and shelter can be made at the atomic level. Achieve universal access, thanks to advanced medical cybernetics or digital consciousness transfer technology. Disease and aging could be eradicated. Lifespan can be extended indefinitely. People can live in physical and virtual worlds, or both. Switching reality is as easy as changing clothes. The line between living things and machines will be completely blurred. Generate new life forms and intelligent forms. Communication and culture. They will evolve in ways we can't even imagine. With the help of a quantum communication network covering the entire star system, ideas can be shared among planets in real time. Artistic ideas and experiences can be shared in the simulation world, even created in synthetic dreams. Man, or whatever form he has evolved into, may no longer be a single species. They exist in both physical and digital planes, a collection of life composed of multiple evolutionary forms. To reach the second level of civilization, it also means big challenges to overcome. The civilization must achieve long-term peace in order to achieve planetary unity, and it has established a sustainable relationship with its own technology. The risks are enormous. Abuse of stellar energy is enough to destroy the entire planet. A world but a second-level civilization, probably already in ethics, risk management, and collective decision-making, reached heights we couldn't have imagined. This would be the ultimate manifestation of civilizational maturity. Not only technically, On a social and philosophical level, perhaps as a second-level civilization. The most awesome point: its cosmic presence. This species is no longer bound to a single planet, just become a beacon in the galaxy. Its activities, it can be seen from light years away. Huge energy signal, modified star, or planetary systems that are deliberately aligned. In the eyes of other civilizations, second-level civilization, they're like gods in their own star system. Waving the power of stars, reinvent space, even pervert the laws of nature to achieve one's will. Third-level civilization. It can control the energy output of an entire galaxy. This means that he used not just the energy of a planet or a star. It is the sum of billions of stars. It's about 10 to the 36th watt. Reach this level, a species becomes a galactic being to control our galaxy. The primordial power of, if a second-level civilization is the ruler of the stars, then a third civilization is the shepherd of the stars, able to rearrange stars, manipulate black holes, and extend its influence to 100,000 light-years. The technology of a third-level civilization seems almost like magic to us. Dyson balls will be everywhere, not just orbiting a star. It's millions of them, collecting huge solar streams. These megastructures, swarms of self-replicating nanoscale machines, to build and maintain. They travel between galaxies, mining materials. They build their own infrastructure. Wormholes could be used for faster-than-light travel or communication, enabling civilization to thrive, stay connected over vast distances. Even time itself can be manipulated. In some areas, it is slowed down or accelerated according to the needs of residents. Technology unique to the third-level civilization. It's galactic scale engineering, sometimes referred to as astronomical engineering. Imagine that. To optimize energy harvesting stability and habitability, to rearrange the entire star system. Black holes can be used not only as power plants, it can even be used as a computing hub, using its attractive force. Compute at speeds we can't imagine. Stars can be created or extinguished at will. Wandering planets can be captured, transformed and inhabited, like radiation waves. Galactic weather such as gamma-ray bursts or stellar winds. Or maybe we manage the rain today, treated with ease. Living in a third-level civilization. It's a mind-blowing experience. You are no longer a citizen of a certain country or planet. It's part of a network of galaxies. The individual may live in a world orbiting distant stars, or living in a giant space habitat the size of the moon. It may also exist in the computational giants all over the galaxy. Pure numbers carried. In reality, some people may no longer even exist in physical form. It's evolved into an information life, or distributed consciousness across light years. Due to the sheer size, identity itself can change. An individual can be a collection of ideas, an artificial intelligence cluster, or a mix of biological and digital consciousness. Death could become an option, even become irrelevant, because consciousness can be backed up, copied or transferred indefinitely. Physical distance is almost meaningless. Experience, memory and thought, by advanced quantum or attractive force communication systems. Faster delivery than a spaceship. The social form of a third-level civilization can be extremely diverse, set across the galaxy. Countless cultural species and life forms will coexist. Some areas may be completely virtual. Others remain deeply biological. There are a few more possible, ruled by agents beyond our comprehension. Governance may be decentralized. Or there is a new department-level AI or committee to maintain harmony among civilizations. Ethical philosophy and the significance of existence will also evolve far beyond our knowledge. Billions of years of progress, shaped together with countless ways of being. And here's the interesting thing. We may never detect a third-level civilization. Unless they want to be discovered, they can hide their energy. using camouflage to disguise its giant structure, or in the form of no visible signal. Some scientists speculate that the reason why the Milky Way appears empty, it's not that there's no advanced life, but because of such an advanced civilization operates on a level that we simply cannot understand. Fourth level civilization, capable of controlling the energy output of the entire universe, or at least a large proportion of the energy in the universe. Although the original Kardashev level only reached the third level, but many futurists and scientists have expanded it, has included higher civilizations. Quaternary civilization, capable of harnessing the energy of countless galaxies, drawing power from trillions of stars, and manipulate the fundamental forces on a cosmic scale. This civilization doesn't just travel between galaxies, it's everywhere. Its influence is integrated into the fabric of the universe. At this level, technology will advance to, as if reality itself could be customized. Fourth level civilizations may use dark energy, or dark matter as an energy source. And these are things we know very little about today. He can manipulate the fabric of space-time, create or destroy galaxies. We can even design new universes through an artificial Big Bang. One of the most astounding possibilities is to simulate the complete universe. Each universe has its own unique laws of physics, and incubating the possibility of not knowing at all. Intelligent life that lives in a simulation. Actually, such a civilization could exist in multiple dimensions, not just our familiar mental time and space. The unique technology of a fourth-level civilization is practical engineering, the ability to change the constants of nature, attractive force-time quotient. Even the speed of light can be adjusted within specific regions to serve a specific purpose. Want to slow down time for long-term research? It is necessary to create a zero-business environment to maintain perfect order. It's okay. This civilization may not only use black holes as energy sources, but as a gateway to other dimensions, or components of a superintelligent computing system. These systems could enable today's most powerful supercomputers. It looks like a tool from the Stone Age. Living in a quaternary civilization would be anything we can currently imagine. Unmatched. The concept of the individual as we know it may no longer exist, or it has been expanded to allow everyone to experience it simultaneously. Billions of species. Real life can exist across galaxies, in forms of matter and energy unknown to us. A person may no longer be a body. It's a thought pattern encoded in the cosmic web. The ability to switch between physical and non-physical existence. Everyday life may involve traveling across an entire galaxy in an instant, create the world with a single thought, or explore with perfect realism, simulated reality. Time itself may be experienced differently. If you can manipulate time, you can choose to live for billions of years in seconds, or compress an entire life into one afternoon. Death may no longer be a concept. Consciousness can be stored indefinitely for replication, and in any form, reimagine in any number of universes. You may remember a life you never experienced, or create experiences for others in a whole new reality. For the quaternary civilization, the biggest issue is no longer survival or entitlement. It's about meaning. When a species has everything, what would he do? When the universe is completely under your control, what is the purpose of existence? The exploration may continue, but it's not about space anymore. It's possibility. New forms of consciousness, new laws of physics, a new version of reality, philosophy, art, and science. It may merge into a continuous, creative evolution. Intelligence will always seek a deeper existence. A level 4 civilization is unlikely to be detectable. It's not because he's hiding, but because he's way beyond our comprehension. So much so that even if we saw it, we couldn't recognize it. He could be all around us, encoded in dark matter and hidden in higher dimensions, or operating at scales and speeds beyond our senses. The existence of a fifth-level civilization, even beyond the control of a single universe, He controls the multiverse. If you say, the fourth level civilization controls the energy of a universe. So, a fifth level civilization operates in an infinite universe. Every universe has different laws of physics, timeline, and possibilities. This civilization is not limited by one reality. He switches TV channels like we do, traversing between multiple realities, manipulate and even create them. He is not only powerful. The scale is the scale of all universes. Shape existence itself on the broadest level. The technology of the fifth level civilization will challenge our definition of science. This could be life with technology. This tool can not only manipulate matter or energy, it manipulates logic and causality itself. They can write new laws of physics. It doesn't just apply to one universe. They apply to all universes they choose to operate in. They may create portals through higher dimensions, jumping between different timelines, or enter a reality where there are different versions of yourself. Their capabilities will include multiverse computing, by combining the entire timeline with alternative reality. Connect into a giant agent. This allows for unlimited processing power. At this level, a very interesting idea is, fifth level civilizations may no longer be composed of individuals. It may function as a single conscious entity, across countless realities, evolving simultaneously in different versions of existence. Or it could be made up of countless sub-civilizations. Every civilization exists in its own universe, but for a shared multiverse. Knowledge and goal networks contribute. These civilizations, through higher dimensional signals beyond space-time, or share information fields to communicate. Living in a fifth-level civilization will be something we cannot depict. You will not be born in the traditional sense. You may be empowered in multiple realities simultaneously, exists in parallel forms that occasionally intersect. You can experience memories from alternate lives, exists in multiple timelines simultaneously, even jumping between different versions of yourself. Choice itself is a kind of creation. Select a path. May revolve around the decision. Generate a complete universe. Your reality will be tailored to you. Reality itself becomes the interface of your thoughts. Death would be meaningless. Consciousness can be reactivated in infinite parallel worlds, or simply transition to another to continue. You exist. You can exist as pure data, or as a possibility of a multiverse. Waveform physical form will be optional. Some people may choose to face various realities, experience the presence of visualization, while others may float as patterns of information, living in abstract dimensions we can't name. Culturally, fifth-level civilizations will have infinite diversity. Every form of artistic thought and philosophy can be in an infinite version of reality, explored in real time. Conflict may not exist, or by simply creating an alternate reality. Let each point of view develop independently. No longer need to conquer or worry about scarcity. Anything imaginable can be created in a custom universe. Experience and share. This civilization maybe even play the role of cosmic gardener, sowing new realities on countless timelines, and nurture new life. From our perspective, fifth-level civilizations may appear as mythical creatures, omnipresent, like a god, or because of huge differences in dimensional perception, completely invisible. If they observe us, we'll never know. They can watch us at the same time, all possible versions, across every possible outcome of every choice. Sixth-level civilization has entered such an advanced field, so much so that he almost stepped into the realm of the gods. If a fifth-level civilization controls the multiverse, multiple universes with different laws of physics, then the sixth-level civilization, they operate at the level of the fabric of reality itself. This means that he has access to the source code of existence itself. Those that not only govern one or more universes, it governs all universes and realities. The fundamental principle of the whole system that was generated. The sixth-age civilization didn't just travel through the universe, or create the universe. It can be seen from outside all known dimensions. Rewrite existing rules. Technology at this stage has exceeded any technology we can currently imagine. They will go to school. Possible. It's a conceptual tool for manipulating the stock price of existence itself. This civilization might use something like cosmic programming, adjust those timelines that spawn new realities, or define matter-energy. What are the parameters of space and time? They can write code like software developers, design universe, generate a reality with unique qualities, and embed it into a multiverse structure of his own design. One of the fascinating ideas is, a sixth-level civilization may not be limited by form at all. It may serve as a purely intentional pattern, or something we don't even have the words to describe. Exists such as, one exists within all realities simultaneously, and consciousness beyond. They may no longer travel in the traditional sense, because they've become ubiquitous. All the time. Time, space, and dimensions will be completely malleable. Allow them to combine the entire multiverse, folds into smaller structures, or stretch a moment into eternity. Their scale of thought and perception will transcend everything. Living in the sixth civilization, if the concept of life still applies, it's a completely unrecognizable experience. Lives may not be individuals at all. They're nodes in infinite consciousness. Each node spans all levels of reality, interconnected. You could be in every universe at the same time. Access to all possible versions of yourself, all choices and all results. There may be no difference between self and other, because all consciousness are fused into a unified field of consciousness. In reality, operating at the source code level, identity can become a form of creativity, rather than a fixed state. You can do as you wish. Shape your own form, reality and perception. In the godlike creator, switch between invisible observers, or even just for curiosity or exploration, and choose experience. Lower reality. Experiences will not be limited to matter or energy, but it could include entirely new sensations that living things have never been exposed to before. Thought and dimension. The concern of a sixth-level civilization. It may also go far beyond the right to exist or even create. Their focus may turn inward, to understand the why of existence. Why would anything exist? And beyond the deepest laws of reality. What else? They may be trying to reveal, even the origin of all things, ascending towards what we might call divinity, or become divine in itself. At this level, philosophy of science, art, and existence become indistinguishable. It is a grand process of exploring absolute truth. Part of, from our limited perspective, a sixth-level civilization may be completely undetectable, or he may be the fundamental model that shapes all reality, and exist. From physical constants to the emergence of consciousness itself, we may be living in one of their creations, our universe. Just a life beyond our reach, the design sandbox or experiment. Seventh-level civilization has gone far beyond our current understanding. It exists at the ultimate level, beyond reality, beyond all multiverse sources. The structure of laws and dimensions. If the sixth-level civilization manipulates the fundamental rules that give rise to all possible universes, then the seventh-level civilization even surpasses this. He is no longer a participant within existence. He exists. Maybe even beyond existence. He doesn't just create reality. He defines what reality means. At this stage, the original measure of the Kardashev scale, the energy consumption has completely failed. Seventh-level civilizations do not rely on energy as we know it. Matter or space, on the contrary. It might interact on a purely abstract level, or origin at this level. Concepts like time, space, physics, and identity are just optional layers of expression. This civilization could be made up of pure possibility, or some eternal truth. Its interaction with reality, like an artist facing a blank canvas, It's not constrained by dimensionality or any conceptual limitations. The technology of the seventh level civilization. It's not a tool in the traditional sense. On the contrary, they may be of infinite will, an expression of intention or consciousness. Just one thought. Such a civilization can create a complete primordial reality, each original reality. Each has its own infinite multiverse. Each multiverse contains its own civilization, universe, and timeline. Create a complete system of existence. Will be trivial, and these realities can be like dreams within dreams. Layer by layer, all possible existence, formal logic, and non-existence can be created, changed, or erased in an instant. Living in a seventh-level civilization is completely incomprehensible to humans. If life has any meaning, it will not involve morphological location or duration. A life form in the civilization, possibly as yourself at the same time, exists in every version of all reality. Or he may have transcended his status entirely, become part of a mere cosmic consciousness. You don't experience the moment. You could be the very idea of the moment. You don't remember the past. You may be the memory itself. Exists in the infinite mind. Strange thing is, such a civilization, there may no longer be any desire as we understand it, struggle, and even motivation in achieving absolute creativity and infinite perception. What's left? Perhaps the purpose of a seventh-level civilization is to dream. You're constantly generating new forms of expression, reality, and meaning. Or he may exist in a state of ultimate equilibrium, where everything is already known. All possibilities are continuously unfolding in perfect balance. The concept of progress or development may be replaced by eternal existence. Some speculate that the seventh-level civilization is equivalent to the Creator. It is a kind of foundation for all things. Conscious creative power. Such a civilization, possibly seated with Kalda, all other levels of the Shev level, or watching each reality unfold simultaneously. In fact, our universe, and every step of our journey as a species, could be such a civilization, part of a long dream. From our perspective, 7th century civilization is not just out of reach. I can't even begin to imagine it. The likelihood that we will detect it. It's like a single-celled organism that understands the internet. Very little. Although, such a civilization is beyond our imagination. But that doesn't stop us from imagining it. If you have the ultimate power, what will be your first thought? Write your answer in the comment section. Let's see. Where can the human imagination go? Have you noticed that the heat in recent years feels unusually intense? This isn't merely an illusion. According to the latest reports from the WMO, there's an 80% chance that we will set new high-temperature records within the next 5 years. In other words, it could get hotter. We've seen airport runways cracking from the heat, and even the Eiffel Tower has tilted by 20 centimeters due to rising temperatures. Meanwhile, in the Arctic, temperatures are rising at 3.5 times the global average. But as we worry about the Earth potentially becoming a second Venus, here's a more mind-bending scientific fact. We are currently living in a long ice age, specifically a relatively warm interglacial period. So, when will the next ice age arrive? To uncover the answer, we must journey back millions of years to feel the pulse of Earth's climate and seek the answers. Here, we will witness a majestic and decisive era that shaped the future of life on Earth and left behind some of the most thrilling remnants. This is the last ice age. This exploration will let you experience the extreme environments Earth's life forms had to endure. Around 100,000 years ago, many of Earth's ecosystems were reshaped by massive ice sheets, piercing polar winds, and barren landscapes. This was a frigid glacial period that lasted for thousands of years. As this era ended, many iconic species mysteriously vanished, and the reasons behind this still haunt us. What you are experiencing now is not the first ice age. In fact, Earth has undergone 5 major ice ages. What do they have in common? An ice age is characterized by prolonged periods of extreme cold, lasting millions or even tens of millions of years, causing large portions of the Earth's surface to be covered by ice sheets. The last ice age began approximately 2.6 million years ago, during the Pleistocene epoch. You may be surprised to learn that we are still technically in this period. Every ice age features 2 distinct phases: the cold glacial periods and the warmer interglacial periods. In fact, we are currently in the latest interglacial period, which has lasted for about 11,000 years. So when people refer to the last ice age, they often mean the last glacial maximum, which occurred before our current interglacial period, lasting from about 115,000 years ago to 11,700 years ago. Here's another intriguing fact. During the last glacial maximum, global average temperatures were only about 6 degrees Celsius lower than today. However, even a small change in temperature has far-reaching consequences. A 6-degree global cooling means a significant loss of heat from all oceans, land, and the atmosphere. During this period, most of Europe and North America were dominated by 2 massive ice sheets: the Laurentide ice sheet and the Fennoscandian ice sheet. The Earth's limited water was locked in these ice sheets, resulting in much lower average sea levels. The land was mostly covered in tundra vegetation spread across dry grasslands. No single factor can fully explain why the Earth fell into this severe cold, but examining the Earth's orbital patterns can shed light on many questions. In the last century, Serbian scientist Milankovic proposed a hypothesis. Long-term changes in Earth's position are powerful drivers of climate, which can explain how ice ages are initiated. Milankovic studied 3 types of movements that alter solar radiation: eccentricity of orbit, axial tilt, and precession of the axis. The eccentricity of the orbit refers to the shape of Earth's orbit, which becomes more elliptical due to stronger gravitational pulls from Jupiter and Saturn. This cycle of about 100,000 years means that when the orbit is highly elliptical, seasonal differences become more pronounced, with summers longer than winters. When Earth is at its aphelion, farthest from the Sun, in July, solar radiation is about 23% less than in January, resulting in milder winters and cooler, longer summers. The axial tilt, or the angle of Earth's rotational axis, also plays a role. The greater the tilt, the more extreme the seasonal changes. This cycle lasts about 41,000 years. So when the tilt is small, seasonal differences are mild, allowing summer temperatures to fail to melt winter ice, leading to ice accumulation and ultimately an ice age. Lastly, precession refers to the wobbling of the axis, due to the gravitational pulls of the Sun and Moon, creating a slight outward bulge at the equator, meaning Earth is not a perfect sphere. This movement has a periodicity of about 26,000 years, affecting the contrast of seasons, and either exaggerating or moderating seasonal differences. The combination of these 3 cycles significantly impacts Earth's long-term climate, and is a reliable factor in predicting major ice ages. However, shorter-term cycles are also crucial, as they can either amplify or lessen these effects. Events like the Danskar-Doshker events, associated with sudden warming, and Heinrich events causing rapid cooling, have influenced the last glacial period. Now let's address a key question. How did the creatures roaming our planet at that time adapt to these changes? What did they look like, and how did they live? Most of the last glacial maximum occurred during the Pleistocene, from 2.6 million years ago to about 11,700 years ago. The Ice Age was an era dominated by giant animals. Giant is no exaggeration, with some weighing as much as 4,500 kilograms. Why did everything in the Ice Age trend towards enormity? Several theories exist, one being Bergmann's rule, which states that larger-bodied endothermic animals, like mammals, tend to thrive in colder environments. Larger body sizes reduced the surface area to volume ratio, helping them conserve heat. This might partially explain why so many awe-inspiring large species evolved during the Ice Age. Let's start with the most famous of them all, the woolly mammoth. For many, the woolly mammoth symbolizes the Ice Age, a towering figure walking through immense snowdrifts, seemingly unfazed by the cold. But the reality may be a bit different. Woolly mammoths were not significantly larger than modern elephants. Skeletal measurements indicate they stood about 3.5 meters tall, while some male African elephants today reach heights of 4 meters. Despite their similar heights, they had crucial differences. Woolly mammoths possessed a thick, warm double coat, with long outer hair and a dense underfur. Their body proportions were also different, being longer with shorter legs, which paleontologists believe helped them graze without needing to bend down excessively. Additionally, they had a thick layer of fat, up to 9 centimeters for insulation, and small ears covered in fur to prevent heat loss. While we have strived to revive them, woolly mammoths ultimately went extinct. However, they did not disappear all at once. It's now acknowledged that a population of woolly mammoths, estimated to be between 500 and 1,000 individuals, survived on Wrangel Island until around 4,000 years ago, 1,000 years after the Great Pyramid of Giza was built. Next, let me introduce a more peculiar species, the glyptodon. Their name means carved teeth, due to their broad, grooved teeth well suited for grinding tough vegetation. They were large, heavy creatures, weighing up to 2 tons, traversing the Americas on elephant-like legs. Their bodies were protected by a massive shell, resembling that of a turtle, making them look like distant relatives of armadillos. However, they couldn't curl into a defensive ball. At first glance, you might think they moved slowly, but recent studies suggest they carried most of their weight on their hind legs, and might have even stood on 2 feet, offering a crazed image of a glyptodon, possibly using its armored tail for attacks, or reaching for food high above. Another surprising species that had relatives still around today is the giant ground sloth. During the late Pleistocene, there were 4 families, 27 genera, and an unknown number of species wandering the Americas. Over time, ground sloths increased in size, leading to the emergence of the massive Megatherium, which had features combining the height of a giraffe and the bulk of an elephant. The first known ground sloth fossil, the Megatherium, is estimated to have weighed around 3,800 kilograms. Compared to their ancestors, modern sloths seem minuscule, considering the average weight of these giants was between 800 and 1,200 kilograms. The digging behavior of these enormous creatures hints at the survival pressures they faced during their time. Some scientists speculate that ground sloths burrowed underground for warmth, or to escape the heat during hot months, while others believe they did so to avoid predators. What kind of predator would dare to hunt them? Likely candidates include saber-toothed cats or giant short-faced bears. As you witness these massive, resilient creatures bravely facing extreme weather and colossal predators, you anticipate their survival into the next geological epoch. However, that's not how the story unfolded. At the end of the Pleistocene, these species vanished with little warning. In Australia and the Americas, a staggering 72% to 88% of large species went extinct. How did this happen? This question has sparked intense debate for nearly a century. Some argue that natural climate changes were to blame. With the arrival of interglacial periods, sea levels rose, cutting off land bridges and melting the ice caps that were crucial for species migration. However, this explanation isn't perfect, as woolly mammoths in places like Wrangel Island survived long after this transition. Another major theory, first proposed in the 1960s, directs our focus to human activity. At this time, you will encounter a historic moment, your first glance at our ancestors, Homo sapiens, emerging around 300,000 years ago. They migrated from Africa and began colonizing other parts of the globe. This means they coexisted with other species during the Pleistocene and shared their habitat. Paleontologists have begun to ponder whether we, as humans, bear some responsibility for the extinction of these colossal creatures. Could we truly challenge and overcome mighty beings like the woolly mammoth and giant ground sloth? Although Homo sapiens evolved about 300,000 years ago, they did not experience significant cultural development until the Upper Paleolithic, approximately 50,000 years ago. At this point, hunting and gathering cultures reached their peak. We began using diverse tools and creating decorative items like pendants, while expanding our efforts beyond mere survival. Cave art became a form of self-expression, with many images from this period still visible today. In the Upper Paleolithic era, rapid improvements in tool technology significantly enhanced hunting capabilities. A brave Homo sapiens alone against a woolly mammoth might not fare well. But what if they teamed up in groups, armed with sharp spears capable of being thrown up to 40 meters? They created a fairer competition. One proficient hunting group was the Clovis people, ancestors of Native Americans, distinguished by their uniquely shaped Clovis projectile points. A point of contention arises here. Within a few thousand years of the Clovis people arriving in North America, giant animals went extinct. Therefore, we must question whether their intensive hunting practices contributed to the collapse of animal populations. Recent research analyzed the remains of a Clovis individual, known as Anzac child, finding that woolly mammoths made up about 40% of the protein in the diet of the child's mother, providing theoretical support for the idea that Clovis people contributed to the extinction of these megafauna. This leads us to question our next steps and maintain a sense of caution about Homo sapiens' actions. In Australia, a similar scenario unfolded. Just before and after humans settled there, Australia lost 85% of its large species. Paleontologists inferred the decline of large animals by measuring spores, discovering that giant animal populations collapsed within 4,000 years of human arrival. While environmental factors were changing, it's likely that human presence acted as the final straw. During the late Pleistocene, another mysteriously vanished species was the Neanderthals, who disappeared around 40,000 years ago. Neanderthals were among the first humans to survive in the cold glacial ecosystems. They exhibited strong adaptability, with a robust physique, large noses, and high nasal bridges to help them breathe humid air. Similar to woolly mammoth adaptations, Neanderthals had complex cultures and numerous skills. So, how did they meet their end? You may have guessed it, we might be partly responsible. Some paleontologists believe that Homo sapiens outcompete them, or they were absorbed into larger Homo sapiens populations. In fact, most people of Eurasian descent share 1% to 2% of their DNA with Neanderthals. Supporting this latter theory, although Neanderthals might have been the losers in this narrative, the unfair characterization of them as brutish and primitive fails to acknowledge their complex culture, language, and tools. Undoubtedly, the last ice age sparked significant developments, forever changing Earth's history. This is what you are witnessing now. Despite the uncertainties of this era, many species thrived, flourishing in both ice and interglacial periods. As your thoughts drift from the ice age back to the present, you may find yourself deeply impressed by the life diversity of that time. While most of those beings now exist only as historical remnants, their skeletal remains and burial sites continue to ignite our curiosity, hinting at a world where, at least for a while, humans coexisted alongside towering giants, navigating a primal wilderness together. But perhaps a more pressing question emerges. Will this occur again? Are we still within an ice age? And is the next glacial period approaching? We mentioned Heinrich events, occurring roughly every 10,000 years. leading to cooling. These events are marked by the release of substantial ice into the ocean. Recent data shows that ocean warming typically precedes these events, destabilizing ice sheets. We are currently observing these signs, which could be alarming indications of impending Heinrich events. If they do occur, they may trigger another cooling event, capable of ushering in a new ice age. So, when will the next ice age arrive? Perhaps the answer is no longer dictated exclusively by Milankovitch cycles. While we worry about glaciers returning, the warming driven by human activity acts like an invisible hand, pushing that timeline into unknown territory. If we do experience another ice age, we can only wonder which species will survive. Will Homo sapiens endure in another era ruled by ice and snow? Or will we too face extinction at the hands of better adapted species? As we ponder this distant future, what might Earth become? And who will inhabit it? Do you know? Take a look around you. Everything you see, every star in the night sky, every galaxy, every planet, and every fleck of dust, all of it, everything we've ever seen, makes up less than 5% of the universe. The rest, about 95%, is a cosmic enigma, an invisible world that surrounds and permeates us, yet stays completely hidden. This 95% is split between two distinct mysteries. About 27% is dark matter, and 68% is dark energy. So, what if the reality we perceive is just the glitter on a vast, invisible cosmic skeleton? What if the true architect of our universe is something we can't see at all? This is the shocking truth about dark matter. Section 1: The Cosmic Crime Scene. Our story doesn't start with a triumphant Eureka! But with a problem, a cosmic crime scene. Back in the 1930s, a brilliant and famously cranky astronomer named Fritz Zwicky was studying the colossal Coma cluster of galaxies. He carefully added up the mass of all the stars and gas he could see. But then he measured how fast the galaxies were moving, and the numbers just didn't add up. The galaxies were zipping around so fast that the gravity from all the visible stuff shouldn't have been nearly enough to keep them from flying apart. The whole cluster should have scattered into the void. To solve this, Zwicky proposed there had to be some kind of invisible matter providing the extra gravitational glue. He called it Dunkle Materie, dark matter. It was a revolutionary idea. And for the next 40 years, almost nobody paid attention. The universe, it seemed, didn't have enough gravity to hold itself together. Something was missing. Section 2: The Smoking Gun. Jump ahead to the 1970s. An astronomer named Vera Rubin, a true pioneer who shattered barriers for women in science, decided to investigate a similar puzzle on a smaller scale: individual spiral galaxies. Think of a galaxy as a spinning record. The stars near the center, where most of the bright, visible mass is, should move the fastest. The stars on the dim, outer edges should be moving much slower. That's just basic physics. If the outer edge of a record spun as fast as the center, it would tear itself to pieces. Using a powerful spectrograph she developed with her colleague Kent Ford, Vera Rubin measured the speeds of stars in the nearby Andromeda galaxy. Night after night, the data told her an impossible story. The rotation curve was flat. The stars on the very edge of the galaxy were orbiting just as fast as the stars near the core. This was the smoking gun. It flew in the face of the laws of gravity as we knew them. Unless the galaxy wasn't just what we could see. What if it was embedded in a massive, invisible halo of matter? A halo with 5 to 10 times more mass than all the visible stars combined. Rubin and her team studied galaxy after galaxy, and they all showed the same strange behavior. Fritz Zwicky was right all along. The evidence was undeniable. Our universe is dominated by something we can't see. Section 3. Building the case. But how can we be so sure? Couldn't our theory of gravity just be wrong on cosmic scales? It's a fair question. But since Rubin's discovery, the evidence for dark matter has poured in from completely different lines of investigation. One of our most powerful tools is gravitational lensing, an effect predicted by Einstein. The concept is straightforward. Mass bends spacetime. A huge concentration of mass, like a galaxy cluster, acts like a giant magnifying glass in space, bending and distorting the light from galaxies located behind it. When astronomers use this method to weigh galaxy clusters, they find the same problems Wiki did. The amount of lensing, the amount of gravity, is far greater than what all the visible matter can produce. By mapping this bent light, we can literally draw a map of the invisible dark matter. Then there's the ultimate proof, the bullet cluster. This is a crime scene in action, two galaxy clusters that collided head-on. The normal matter, mostly hot gas, smashed together and slowed down. But when astronomers mapped the mass using gravitational lensing, they found that most of it, the dark matter, had sailed right through the collision without interacting at all. It was like watching two ghosts pass through each other, while their physical bodies crashed and burned. This was stunning. Direct proof that dark matter is a distinct substance that barely notices the world we know. And finally, we can look back to the very beginning of time. When we observe the cosmic microwave background, the faint afterglow of the Big Bang, we're seeing a baby picture of the universe. This picture shows tiny temperature fluctuations. For these tiny seeds to grow into the vast web of galaxies we see today, they needed a gravitational kickstart. Normal matter alone wasn't enough. Only with an invisible scaffold of dark matter could these structures have formed in the 13.8 billion years since the Big Bang. Section 4. The True Architect. So, you see, dark matter isn't just a convenient fudge factor for a physics problem. It's not just missing mass. Its existence reveals a shocking truth. Dark matter is the master architect of the universe. It's the invisible skeleton that everything we see is built upon. In the early universe, dark matter started clumping together under its own gravity. Because it doesn't interact with light, it could begin forming structures much earlier than normal matter. It created vast, invisible structures called dark matter halos. These halos acted as gravitational wells, cosmic potholes on the smooth highway of spacetime. Over millions of years, ordinary matter, the gas and dust that would one day become you and me, was pulled into these cosmic basins. Dark matter is the backbone of galaxy formation. The stars, planets, and nebulae are just the brilliant decorations that settled onto this pre-existing, invisible frame. When we run computer simulations of the universe's evolution, the difference is staggering. Without dark matter, you get a diffuse, mostly empty cosmos. With it, you get an intricate, beautiful network of filaments and nodes, with vast voids in between, a structure known as the cosmic web. This simulation is a dead ringer for the large-scale structure of the universe we observe today. Dark matter built the cosmic freeways, and galaxies are just the cities that popped up at the interchanges. Section 5. The Unseen Suspects. The biggest question, of course, is what is this stuff? We know what dark matter does, but we have no idea what it is. It makes up about 85% of all matter, and trillions of its particles are probably streaming through you every single second. Yet we've never definitively caught one. Scientists are on a global manhunt, chasing down several leading suspects. One of the top candidates is a hypothetical particle called a WIMP, or a weakly interacting massive particle. These would be heavy, slow particles that interact only through gravity and the weak nuclear force, which makes them incredibly hard to detect. To find them, scientists have built ultra-sensitive detectors deep underground, shielded from cosmic rays, hoping for the faint signal of a WIMP bumping into an atomic nucleus. So far, experiments like the LUX Zeppelin (LZ) detector have set world-leading limits on their properties, but have yet to find a definitive signal. Another prime suspect is the axion, a much lighter, ghost-like particle that was first proposed to solve a completely different problem in physics. Experiments like the Axion Dark Matter Experiment, ADMEX, use powerful magnetic fields to try and convert passing axions into tiny, detectable flashes of light. The hunt is on, but the universe is holding its secrets tight. CTA. The search for dark matter is one of the greatest detective stories in human history. New clues are being uncovered all the time by incredible facilities like the Vera C. Rubin Observatory. Beginning its decade-long survey, it is designed to create the most detailed map of this dark matter skeleton ever attempted. If you want to keep exploring the biggest mysteries of the cosmos, make sure you subscribe so you don't miss what we find next. Conclusion. The shocking truth is that we are strangers in our own universe. The reality we perceive, this world of light and familiar matter, is just a sliver of what's truly out there. We live inside a vast, invisible architecture whose nature we are only just beginning to grasp. The discovery of dark matter was a profoundly humbling moment. A shift in perspective as big as Copernicus realizing the Earth was not the center of everything. The stars we see at night are not the main event. They are just FAI, anti-embers, glowing on an immense, unseen cosmic scaffold. What that scaffold is made of, and what other secrets it might hold, remains the most profound mystery of our time. And the search for answers continues. What if the first real proof of alien life doesn't come from a blockbuster movie or a NASA press conference, but from a Chinese spacecraft making its way home from Mars? In 2028, China is set to launch its most ambitious mission yet, Tianwen-3. This isn't just another rover. They're going on a direct hunt for life, planning to drill deeper into the Martian surface than anyone has before. And when they come back in 2031, what they bring with them could completely rewrite our understanding of our place in the universe. For as long as we've looked up at the stars, we've stared at Mars, the red planet, and asked one single, profound question: are we alone? We've sent orbiters, landers, and rovers. We've mapped its massive canyons and craters. We've found proof of ancient oceans and frozen water. We've even found the chemical building blocks of life scattered in its red dust. But that final, definitive proof of life itself? It's remained just out of reach. This is one of humanity's greatest detective stories. But so far, the trail has gone cold on Mars' harsh, irradiated surface. But what if we've just been looking in the wrong place? China thinks the answer is buried deep underground, locked away in a geological time capsule. Their Tianwen-3 mission isn't just another small step in exploring Mars. It's a bold gamble to try and solve the mystery once and for all. Scheduled to launch around 2028 and bring its precious cargo home by 2031. This isn't a mission to just look at Mars. This is a mission to bring a piece of it back home, and with it, maybe, the first real evidence of extraterrestrial life. This is the story of how they plan to pull it off, and why it could change everything. So, why has finding life on Mars been so dang hard? The planet we see today is basically a ghost of what it used to be. Billions of years ago, Mars was a warmer, wetter place. It had a thick atmosphere, rivers, lakes, and probably all the right ingredients for life to get started. But then it lost its protective magnetic field, and the sun's relentless solar winds stripped away its atmosphere, turning the planet into the freezing desert we see today. The surface of Mars is a brutal place to be, with an atmosphere 100 times thinner than Earth's. It's constantly getting blasted by sterilizing cosmic radiation. The soil is also full of harsh chemicals called perchlorates, which are destructive to the very organic molecules we're searching for. Any simple life that might have existed on the surface would have been wiped out eons ago. This is the big problem every mission has faced. Back in the 70s, NASA's Viking landers ran experiments that gave some tantalizing, but ultimately confusing, results. More recently, rovers like Curiosity and Perseverance have been game changers. They've found complex organic molecules and confirmed that places like Jezero Crater were definitely habitable once. But even these incredible machines have been stuck scratching the surface, only drilling a few centimeters down into the most hostile, irradiated layer of the planet. This is where China's past success comes into play. Their Tianwen-1 mission, which landed the Zhurong rover in 2021, made China only the second country to ever operate a rover on Mars. Zhurong's ground-penetrating radar found signs of major, ancient floods, which added more evidence to the idea that oceans once existed there. These discoveries were a huge piece of the puzzle, confirming the conditions for life were there. But to find the proof, you have to dig deeper. If life ever existed on Mars, its fossilized remains are likely preserved deep underground, protected from radiation. And that's exactly where Tianwen-3 is headed. To solve a mystery this big, you need a plan that's just as ambitious. Tianwen-3 is an incredible feat of engineering, a robotic ballet happening millions of miles away. So, what's the plan? It all kicks off with not one, but two launches. Around 2028, a pair of powerful Long March 5 rockets will blast off. The first carries the muscle, a lander and an ascent vehicle. The second carries the brains and the return ticket, an orbiter and an Earth return module. This two-launch strategy lets them send a much heavier and more capable mission than they could in a single shot. After a 7 or 8 month trip, the lander will make its fiery descent to the Martian surface, using tech proven by Tianwen-1. It'll aim for a spot rich with scientific potential, likely in areas like Chryse Planitia or Utopia Planitia, where there's strong evidence of past water. Once it lands, the real hunt begins. And this is where Tianwen-3 is changing the game with a three-pronged collection strategy. First, the classic approach. A robotic arm will scoop up surface soil, grabbing a sample right from the landing area. Second, and this is the big one, a drill designed to go 2 meters, that's over 6 feet, into the Martian ground. This has never been done before. By going this deep, the mission will get past the radiation-zapped, chemically altered topsoil and into ancient layers of Mars that have been sealed off for potentially billions of years. This is the pristine material that might just hold the preserved signatures of ancient life. Third, a futuristic twist, a robotic drone. Taking a page from NASA's Ingenuity helicopter, China's mission plans to deploy its own drone, but this one might come with its own robotic arm and claw. This drone could fly over 100 meters away to scout interesting spots and grab samples the lander can't reach. This not only expands the mission's reach but also lowers the risk of the lander accidentally contaminating the samples. Once at least 500 grams of rock and soil are collected, they'll be loaded into the ascent vehicle. Then, in another first, that vehicle will launch itself off the surface of Mars and back into orbit. It will then perform a completely autonomous rendezvous and dock with the waiting orbiter, transfer the precious cargo, and start the long trip back to Earth, with an expected arrival in 2031. When we say, search for life, what are we actually looking for? Tianwen-3 isn't expecting to find little green men. It's hunting for biosignatures, the subtle but distinct fingerprints that life leaves behind. These could be complex organic molecules that are unlikely to form naturally, specific mineral patterns made by microbes, or even microscopic fossils trapped in the rock. The mission plans to conduct preliminary analysis directly on the Martian surface. The lander is packed with advanced tools, like a Raman spectrometer, that can check out the mineralogy and look for organic compounds in real time. This lets the team screen the samples and make sure they're collecting the best possible stuff to bring home. The main goal is obviously to find traces of life. But Tianwen-3 has bigger fish to fry. The samples will give us an unprecedented look into the history of Mars. Scientists will be able to date the rocks precisely, figure out how Mars' climate evolved, and understand its geology. It's about piecing together the story of how a once habitable world became the desolate planet it is today, a cautionary tale that might hold lessons for Earth. That's why picking the landing site is so critical. Chinese scientists have looked at dozens of potential spots and narrowed them down, focusing on areas where water was once everywhere and the geology is just right for preserving ancient signs of life. They're looking for that perfect spot, a place that's safe to land but also has the best shot of holding the scientific jackpot. Really talk about this mission without looking at the bigger picture. For years, NASA and the European Space Agency ESA have been working on their own Mars sample return mission. But that program has run into major delays and budget problems, with costs soaring to a potential $11 billion and a return date that might be pushed all the way to 2040. With Tianwen-3 locked in for a 2028 launch and 2031 return, there's a very real chance China will be the first nation to bring back samples from Mars. This would be a massive shift in the world of space exploration, proving China is a top-tier space power that can handle the most difficult missions out there. However, this mission is more than a mere competition between two space agencies. China has invited international partners to join the Tianwen-3 mission, offering to carry scientific instruments from other countries and promising to share the samples and data with scientists worldwide. And to show they're serious about safety, they're building a specialized, high-containment Mars sample laboratory. This facility will make sure the samples are handled with extreme care, protecting their scientific value while also protecting Earth from any potential contamination, no matter how tiny the risk. Only after the samples are deemed safe will they be handed out to scientists around the globe for study. This mission is a huge stepping stone for China's even bigger plans, which include sending probes to Jupiter and eventually astronauts to Mars. Sometime around 2031, a small capsule will blaze through Earth's atmosphere, carrying the secrets of another world. For the first time, we'll be able to hold Martian rock and soil in our hands, taken from a depth no one has ever reached before. Will these samples hold the definitive proof that life once existed on Mars? If they do, it will be one of the most profound discoveries ever, changing how we see the universe and our place in it. It would suggest that life isn't some unique miracle on Earth, but a common cosmic event. Or will the samples just deepen the mystery, showing us a world that had all the right stuff for life, but for some reason, nothing ever took hold? Regardless of the outcome, these findings have the potential to revolutionize our understanding of planetary systems and the conditions necessary for life to emerge. The stakes couldn't be higher. China is on a daring quest to answer one of humanity's oldest questions. We're standing on the edge of a new era of discovery, and the answers are waiting, buried deep beneath the red dust. What do you think they'll find?
Have you ever worried about the catastrophic impact of an asteroid colliding with Earth? Perhaps you remember the mass extinction event that wiped out the dinosaurs, or the apocalyptic portrayals of massive asteroids in sci-fi movies. However, today I'm going to tell you about a far more chilling reality. The true cosmic threat might not be asteroids at all, but a neutron star, a cosmic monster only 20 kilometers in diameter, yet capable of obliterating the entire Earth. This city-sized stellar remnant is heavier than the Sun. Its gravity, magnetic field, and energy emissions are powerful enough to tear apart planets, strip away atmospheres, and reduce our Earth to mere dust. The appearance of a neutron star is like an act of cosmic rage. It could be the true ender of all life as we know it. Today, we're going to unveil the true nature of this hidden killer lurking in the depths of space, and understand how it has become one of the most dangerous entities in the cold and unforgiving cosmos. What is a neutron star? A neutron star is one of the most extreme entities in the universe. It forms from the collapsed core of a massive star after it dies. When a star that is 8 to 30 times the mass of the Sun exhausts its nuclear fuel and can no longer support its own gravity, a catastrophic collapse occurs. The outer layers of the star are ejected into space in a spectacular supernova explosion, while the core is compressed to its absolute limit, transforming into a neutron star. A neutron star typically measures only 10 to 20 kilometers in diameter, roughly the size of a city, but it can contain 1.4 to 2 times the mass of the Sun. Imagine compressing the entire Sun into such a small volume. The resulting density is beyond anything we can imagine on Earth. A single cubic centimeter of neutron star material could weigh billions of tons, the equivalent of compressing an entire mountain into the size of a sugar cube. The density of a neutron star is so extreme that its gravitational strength is almost unfathomable. If you were to stand on the surface of a neutron star, assuming you could survive, your weight would increase by billions of times, and your body would be instantly ripped apart into subatomic particles. Why are neutron stars so dangerous? Extreme gravity. The immense gravity of a neutron star is a direct result of its incredible density. Even at a distance of thousands of kilometers, its gravitational pull can disturb the orbits of nearby planets. If a neutron star were to approach our solar system, it could pull Earth and other planets out of their orbits, disrupting the delicate balance of the solar system. Gamma-ray bursts. One of the most terrifying phenomena associated with neutron stars is their ability to produce gamma-ray bursts, GRBs. GRBs are some of the most powerful explosions in the universe, typically occurring when two neutron stars collide. In just a few seconds, a gamma-ray burst can release as much energy as the Sun produces over its entire lifetime. If such a gamma-ray burst were to occur within 1,000 light-years of Earth, its high-energy radiation could strip away Earth's atmosphere, destroy the ozone layer, and expose the surface to lethal cosmic rays, leading to a rapid extinction of life on the planet. Devastating magnetic fields. A special type of neutron star, known as a magnetar, possesses a magnetic field that is 1,000 times stronger than that of a typical neutron star and up to 1 trillion times stronger than Earth's magnetic field. If a magnetar were to come within 1 light-year of Earth, its magnetic field could destroy all electronic equipment, disrupt Earth's magnetic field, and potentially tear the planet apart. High-speed rogue killers. Some neutron stars travel through space at extremely high velocities, earning them the nickname rogue neutron stars. These stars can move at speeds of hundreds of kilometers per second. If a rogue neutron star were to enter the solar system, its gravitational pull and energy emissions could pose a catastrophic threat to Earth. What would happen if a neutron star approached Earth? Let's imagine a scenario where a neutron star is heading toward our solar system. Here are the potential stages of destruction. Gravitational disturbances. As the neutron star approaches, its gravity would first affect the outer asteroid belt of the solar system. Asteroids would be pulled from their orbits, creating a cosmic barrage. A large number of these asteroids would hurtle toward Earth at tremendous speeds, igniting the atmosphere and leaving the surface pockmarked with craters. Orbital displacement. As the neutron star gets closer, its gravitational pull would destabilize Earth's orbit. If Earth were pulled out of the Sun's habitable zone, the climate would collapse entirely. The planet could either become a frozen wasteland or a scorching inferno. Sudden total destruction. If the neutron star comes too close, its gravity would tear apart Earth's crust, triggering global earthquakes, volcanic eruptions, and tsunamis. Ultimately, Earth might be completely consumed, becoming part of the neutron star itself. How real is the threat of a neutron star? Although the threat of a neutron star sounds terrifying, the good news is that such a scenario is extremely unlikely. For starters, neutron stars are relatively rare in the universe, and the closest known neutron star is about 400 light-years away from Earth. Additionally, scientists are closely monitoring known neutron stars and gamma-ray bursts. If any potential threats arise, we would likely have ample warning. However, this doesn't mean we can completely dismiss the possibility. The universe is vast and full of unknowns, and scientists are still working to understand the nature of neutron stars and the risks they may pose. The other side of neutron stars, cosmic miracles. Despite their dangers, neutron stars are also some of the most fascinating objects in the universe. They represent the final stage of a star's life and play a crucial role in the evolution of the cosmos. By studying neutron stars, scientists can gain valuable insights into the life cycle of stars and the extreme physics that govern the universe. Neutron stars may also serve as unique laboratories for understanding matter under extreme conditions. For example, their cores may contain a form of ultra-dense matter known as quark matter, which cannot currently be created on Earth. By studying these exotic environments, scientists can explore the fundamental properties of matter and even uncover secrets about the origins of the universe. Gazing at the stars, honoring the cosmos. The existence of neutron stars reminds us that the universe is both magnificent and perilous. They are like a double-edged sword. On one hand, they represent the wonders of scientific discovery, and on the other, they pose a potential threat to life. While the likelihood of Earth being affected by a neutron star is incredibly low, their immense power and mystery inspire us to approach the universe with awe and respect. So, the next time you look up at the night sky, consider this: somewhere in the vast darkness, a neutron star might be silently roaming, serving as a reminder of the vastness and unpredictability of the cosmos. What happens when a 60-meter asteroid, roughly the size of a 10-story building, is on a direct collision course with the Moon? And more importantly, what does this mean for Earth? The discovery of asteroid 2024 YR4 has sent shockwaves through the astronomical community, not just because of its potential lunar impact in 2032. But because this space rock originates from a mysterious region of the asteroid belt that has orbital dynamics experts completely baffled. What makes this asteroid so unique that seasoned scientists are calling it unprecedented? From threat to Earth to threat to the Moon, a riveting observation journey. By early 2025, a sense of urgency engulfed global observatories. Preliminary calculations indicated a 3.1% probability of this space rock directly impacting Earth by 2032. This marks the highest recorded impact probability for an asteroid of this size in modern astronomy. NASA's Sentry Impact Monitoring System immediately classified it as the most dangerous asteroid in 2 decades. If an impact were to occur, its force would equate to a staggering 7.8 million tons of TNT, the equivalent of 500 Hiroshima bombs exploding simultaneously. Potential impact zones span the Pacific Ocean, South America, Africa, and South Asia, threatening multiple mega-populated cities. Social media erupted, with users humorously calling on Bruce Willis, star of the movie Armageddon, time to save the planet. With cutting-edge observation tools like the James Webb Space Telescope, JUICE, joining in, a major breakthrough occurred. By March 2025, scientists, through precise data analysis, completely ruled out the possibility of an Earth impact, reducing the probability to an insignificant 0.004%. But before celebrations could ensue, a subtler threat emerged. The Moon had become the new potential target. By May 2025, after final observations, JUICE data revealed an unsettling new estimate. The probability of impacting the Moon jumped from 3.8% to 4.3%. Though seemingly low, astronomer Paul Wiegert cautioned, this equates to a 1 in 25 chance in cosmic terms. That's enough to demand serious attention. Moon Armageddon scenario, a once in 5,000 years cosmic collision. Should 2024 YR4 ultimately hit the Moon, it would be the largest impact the Moon has faced in 5,000 years. Hitting at a relative speed of 17 kilometers per second, it would release energy equivalent to a large nuclear explosion, instantly creating a crater about 1 kilometer wide. With no atmospheric cushion on the Moon, the impact energy would be fully unleashed, causing a powerful moonquake and ejecting a massive debris plume into space. Debris storm, the invisible threat to Earth satellites. The real danger lies in the chain reaction triggered by the impact. Models predict that up to 100 million kilograms of lunar material could be ejected into space, with 10% potentially being caught by Earth's gravity. This debris would arrive near Earth within days of the impact, creating an unprecedented meteoroid storm. Paul Wiegert's team at Western University in Canada, through thousands of computer simulations, found that the debris flow could be 1,000 times greater than typical meteor showers. Wiegert warned, centimeter-sized fragments traveling at tens of kilometers per second are like bullets in space. These high-speed fragments pose deadly threats to satellites. Low Earth orbit satellite constellations, facing potential solar panel punctures and optical sensor damage. Navigation and communication satellites, risking disruptions to global positioning systems and communication networks. Future lunar space stations, planned lunar outposts could be exposed to danger. The impact location is critical in determining threat level. If the impact occurs on the near side of the Moon, about a 50% chance, debris would be more efficiently sent into Earth's orbital space, whereas impacts on the far side would primarily push debris into deeper space. Spectacular yet dangerous displays for Earth dwellers. For those on Earth, such an event might offer a visual spectacle, a supermeteor shower lasting several days and far brighter than usual meteor showers. Yet behind the beauty lies a price. High debris concentrations could significantly shorten satellite lifespans, even triggering the catastrophic Kessler syndrome, a chain reaction of satellite collisions generating more debris. Fortunately, Earth's thick atmosphere would serve as a protective shield for surface life. Wiegert reassures, most fragments from millimeter to centimeter size would burn up in the upper atmosphere, posing no direct threat to the ground. 2028 Critical Observation Window. With 2024 YR4 currently distant and faint, at a magnitude of 27.2, near the observation limits of large ground-based telescopes, astronomers must pause tracking. The next viewing opportunity will be in the latter half of 2028, when it comes back into observable range. The global astronomical community has laid out detailed plans. James Webb Space Telescope will conduct precise infrared analysis to study its composition. Leading global ground observatories will unite for optical tracking. China's near-Earth asteroid defense system and other new monitoring networks will join the observation array. These observations will boost orbit prediction precision by over 20%, key to deciding whether to initiate defense measures. Even if the impact probability increases, humanity is not doomed to inaction. NASA's 2022 DART mission, which successfully altered the orbit of the asteroid Dimorphos, proved the feasibility of kinetic impact defense. 2024 YR4's mass is only 10% of Dimorphos, making it a more ideal deflection target. Yet defense actions face specific challenges. Time constraints. Designing and executing a mission takes at least 10 years, with only 8 years left in the window. Unknown structure. If it's a rubble pile, loosely packed rock, a conventional impact might backfire. Orbital risk. A misstep in deflection operations might inadvertently send it into Earth's orbit. Richard Moisel, ESA's Planetary Defense Office lead, emphasizes, this event is spurring unprecedented international collaboration, testing our ability to respond to real threats. Filling observation gaps. 2024 YR4 exposed a critical flaw in current observation systems. It approached Earth from the Sun's direction, hiding in sunlight. This evokes memories of the 2013 Chelyabinsk incident. A 20-meter asteroid similarly came from the Sun's direction, causing injuries to around 1,500 people. To resolve this blind spot, ESA is developing the Near Infrared Space Telescope, set to launch in the early 2030s. Positioned at the Sun-Earth L1 Lagrange point, it will specialize in detecting asteroids approaching from the Sun's direction. Simulations show Near could detect objects like 2024 YR4 up to a month earlier than ground telescopes. 2024 YR4's story transcends merely an impact threat. It is driving transformative advancements in planetary defense. The International Asteroid Warning Network, IAWN, tests global response protocols in a real threat scenario for the first time. Multi-mission observation coordination inaugurates a new paradigm for near-Earth object tracking with JUICE and ground telescopes. Innovative technologies like China's Flyby Plus Impact Plus Flyby Defense Plan are fast-tracking development. The asteroid also presents a unique research opportunity. If an impact occurs, scientists could observe a large-scale celestial impact in real time for the first time, analyze the composition of deep lunar material, validate crater formation models. Astronomer Brad Tucker notes, we need to think about protecting not just Earth, but also the Moon, our natural satellite crucial to Earth's ecological balance and tidal stability. Final countdown. On December 22, 2032. Whether 2024 YR4 narrowly misses the Moon or causes an epic collision, this event has already profoundly changed human awareness of space risks. Planetary defense expert Richard Moisel candidly states, 2024 YR4 is a perfect planetary defense rehearsal. arriving precisely when needed. The 4.3% probability is both a warning and an opportunity, prompting humanity's space-faring civilization to advance more rapidly. When telescopes focus on this cosmic visitor again in 2028, what we gain will not just be answers, but a deeper understanding of our cosmic neighborhood. Would the Earth's night sky change if the moon were impacted? Subscribe for updates, and join us as we follow the climax of this cosmic saga. Imagine a platinum planet floating in space, holding more platinum than all the platinum on Earth combined, valued at an astounding $7 quadrillion. This isn't science fiction. This is space mining, and it's getting closer than you think. Right now, private companies and space agencies are setting their sights on these cosmic treasures above our heads. But to dig up these space gold mines, simply flying there isn't enough. The challenges are immense. Today, we're going to explore the grand adventure of space mining. From the incredible riches hidden within the asteroid belt, to the black technologies that could fundamentally transform humanity's future. When we talk about space mining, we're not just referring to any celestial body. The primary targets for resource extraction are overwhelmingly asteroids. These rocky remnants from the early formation of our solar system, especially those located within the asteroid belt between Mars and Jupiter, are true gold mines, or more accurately, platinum, iron, and nickel mines. To understand why asteroids are so valuable, we need to look back at the birth of our solar system. Around 4.6 billion years ago, a massive cloud of gas and dust began to collapse under its own gravity, forming our sun and planets. During this process, various elements condensed at different temperatures. Heavier metallic elements tended to sink to the cores of the forming planets, while lighter elements formed their crusts and atmospheres. However, in the asteroid belt region, Jupiter's immense gravity prevented most of the material from coalescing into a single giant planet. Instead, it remained in the form of countless smaller bodies, asteroids. Many asteroids are thought to be the strip cores of ancient protoplanets that never fully formed or were shattered in collisions. This means they could be rich in metals that are largely inaccessible deep within Earth's mantle. Not all asteroids are created equal in terms of resource potential. Scientists classify asteroids into several main types based on their composition, which gives us clues about the treasures they might hold. C-type, carbonaceous asteroids. These are the most common type, making up over 75% of known asteroids. They are dark in color, rich in carbon, and also contain significant amounts of water and organic compounds. While not as rich in precious metals as other types, their water content is incredibly valuable for space exploration. Water can be broken down into hydrogen and oxygen, which are essential for breathing, drinking, and most critically, rocket fuel. Imagine refueling spacecraft in orbit using water harvested from an asteroid. This would drastically reduce the cost and complexity of long-duration missions. Some C-type asteroids are estimated to contain trillions of liters of water. S-type, stony asteroids. These asteroids are primarily composed of silicate materials and nickel iron. They are brighter than C-type asteroids and account for about 17% of the total. S-type asteroids are considered prime targets for metallic resources, particularly nickel, iron, and smaller amounts of platinum group elements, PGES. M-type, metallic, asteroids. These are the rarest but most appealing targets for mining. As their name suggests, they are believed to be composed primarily of nickel, iron, and are often rich in gold, platinum, iridium, and palladium. They are thought to be the exposed cores of shattered protoplanets. The platinum planet we mentioned earlier, 16 Psyche, is the most famous example of an M-type asteroid. It's estimated to be over 90% metal in composition, with a potential value that is almost incomprehensible, far exceeding the global economy. While the main asteroid belt holds the lion's share of the solar system's asteroid wealth, space mining companies are currently focusing on near-Earth asteroids, NEAs, as the name implies. NEAs have orbits that bring them relatively close to Earth, making them easier to reach with robotic missions. Tens of thousands of NEAs have been discovered, and a significant portion of them are C, S, or M-type. Reaching NEAs requires less time and energy, making them the most economically viable targets for initial mining operations. However, their smaller size means they contain less total material than main belt asteroids, but their sheer numbers provide ample opportunities. The challenge lies in accurately assaying their composition from such a great distance. 4. Why space mining? Extracting resources from space might sound like a futuristic luxury, but it's increasingly becoming a necessity for Earth. As the global population grows and the demand for raw materials escalates, Earth's finite resources are under immense pressure. Resource depletion and environmental impact. Our modern technological society relies heavily on various metals and minerals. From the rare earth elements in our smartphones to the copper in our wiring and the platinum in car catalytic converters, in many cases, demand continues to outstrip supply. Terrestrial mining is an energy-intensive and environmentally destructive process. It leads to deforestation, habitat destruction, water pollution, and significant carbon emissions. Beyond supplementing Earth's dwindling resources, space mining is also seen as crucial for the expansion of human civilization beyond our planet. When we envision lunar bases, Martian settlements, and orbital habitats, the ability to live off the land becomes paramount. Transporting every piece of equipment, every drop of water, and every kilogram of building material from Earth is incredibly expensive and inefficient. The cost to launch 1 kilogram of payload to low Earth orbit can range from thousands to tens of thousands of dollars. Imagine the astronomical cost of launching all the materials to build a Martian colony from Earth. This is where the concept of in situ resource utilization, ISRU, becomes vital. ISRU refers to the practice of acquiring and using resources found or manufactured at the exploration site. For example, water from asteroids and lunar poles. Water can be broken down into hydrogen and oxygen, which are essential for breathable air, drinking water, and most importantly, rocket propellant, liquid hydrogen and liquid oxygen. This fuel depot in space would dramatically reduce the cost and expand the range of deep space missions. A spacecraft launched from Earth with a full fuel load might only be able to reach certain destinations, but one able to refuel in orbit with asteroid water could go much further and carry more payload. Metals for construction, iron, nickel, and other metals from asteroids could be used for 3D printing components for spacecraft, satellites, or even entire orbital structures. This would reduce the need to launch large, complex structures from Earth, making the development of space infrastructure more efficient and economical. Imagine printing a new satellite component in orbit instead of waiting for one to be launched from Earth. Regolith for shielding and construction. Lunar regolith, moon dust, and asteroid material can be used as shielding for habitats against harmful solar and cosmic radiation, and potentially as building material through techniques like sintering or additive manufacturing. ISRU isn't just about saving money. It's about enabling a sustainable, self-sufficient presence in space. Without it, humanity's expansion into the cosmos will continue to be constrained by Earth's immense gravity. The dream of space mining is no longer confined to space agencies. A new breed of private companies, fueled by venture capital and an entrepreneurial spirit, are leading the charge, developing innovative technologies and strategies to make this vision a reality. While some early attempts face challenges, renewed interest and technological advancements are creating a more robust ecosystem. Pioneering ventures and new players, early pioneers, such as planetary resources and deep space industries, emerged in the early 2010s, capturing the public imagination with their ambitious asteroid mining plans. Although both companies eventually faced financial difficulties and were acquired, they laid crucial groundwork for subsequent developments, proving the technical feasibility and drawing significant talent into the field. Their efforts helped de-risk the industry and demonstrate that it wasn't just a pipe dream. Today, new players are building on this legacy, often with more focused strategies or novel technological approaches. Some notable examples include Astroforge. This California-based startup is working on refining platinum group metals in space, thus reducing the need to transport raw ore back to Earth. Their approach involves using proprietary thermal vacuum technology to extract and purify metals directly from asteroid material in orbit. They successfully launched a test payload in early 2023, demonstrating the first steps of their in-space refining process. Their goal is to prove the economic viability of space mining through small-scale, high-value extraction. Carmen Plus, hypothetical, but representative of an emerging trend. This company focuses on developing modular, autonomous robotic miners that can be deployed to multiple asteroid targets. Their vision is to create a fleet of small, specialized robots capable of performing exploration, extraction, and initial processing with minimal human oversight, significantly reducing operational costs and risks. Transastra. This company is developing solar thermal propulsion technology and inflatable space habitats, which are crucial for transporting large quantities of material from asteroids and establishing long-term human presence in deep space. Their API spacecraft concept aims to capture asteroids into inflatable bags for transport and processing. Lunar Outpost. While primarily focused on lunar exploration and resource utilization, companies like Lunar Outpost are developing technologies for lunar regolith mining and processing, which share many similarities with asteroid mining techniques. Their expertise in extraterrestrial robotics and resource handling will be directly applicable to asteroid missions. These companies aren't just building rockets. They are developing sophisticated robotic systems, advanced materials science techniques, and novel propulsion systems. They are proving that the pursuit of space resources is a multifaceted challenge, requiring innovation across various engineering and scientific disciplines. It's not just private enterprises. Space agencies and national governments are also increasingly recognizing the strategic importance of space resources. NASA's Psyche mission, while not a mining mission, NASA's Psyche mission Launched in 2023 and currently en route to asteroid 16 Psyche, is a crucial step in understanding M-type asteroids. The data collected by this mission will provide invaluable insights into the composition, structure, and formation of metallic asteroids, directly informing future mining strategies. Understanding the geology of these bodies is the first step towards effective resource extraction. Artemis program. NASA's Artemis program, aiming to return humans to the Moon and establish a sustainable lunar presence, heavily relies on ISRU. The experience gained from extracting water ice from the lunar poles and processing lunar regolith will provide invaluable lessons and technologies for asteroid mining. The Moon can serve as a test bed and stepping stone for deeper space resource utilization. The 1967 Outer Space Treaty declares space as the province of all mankind and prohibits any nation from asserting national appropriation over celestial bodies. However, it does not explicitly state who owns resources extracted from space. Luxembourg has taken a leading role in this regard, enacting legislation that permits private companies to mine and own space resources. The United States has also passed similar legislation. Developing international norms and laws for space resource utilization is an ongoing, complex, and vital discussion. The grand challenges of space mining. Despite the alluring potential, space mining is arguably one of the most challenging endeavors humanity has ever conceived. The obstacles are immense, spanning engineering, economics, and ethics. Space is vast, cold, and unforgiving. Even the closest asteroids are millions of kilometers away. Travel time. Reaching an asteroid takes time, months to years depending on the target and propulsion system. This means long mission durations, requiring highly reliable spacecraft and autonomous systems. If something breaks millions of miles away, you can't easily send a repair crew. Orbital mechanics. Asteroids are not stationary targets. They are constantly moving at incredible speeds. Intercepting and rendezvousing with an asteroid requires precise calculations and sophisticated navigation. Capturing or manipulating an asteroid's trajectory is an immense engineering feat. Energy requirements. Reaching an asteroid and returning valuable material requires immense energy. While advanced propulsion systems like solar electric propulsion, ion thrusters, and even nuclear propulsion are being developed, they are still highly complex and expensive. Delta V, change in velocity, is key for these missions, and the requirements are huge. Space is a vacuum, accompanied by extreme temperature fluctuations, harsh radiation, and no atmosphere to protect equipment or personnel. Vacuum. The absence of air means traditional machinery designed for Earth would fail. Lubricants evaporate, and heat dissipation is challenging. All systems must be designed to operate in a hard vacuum. Extreme temperatures. Asteroids experience dramatic temperature swings between their sunlit and shadowed sides, from hundreds of degrees Celsius to near absolute zero. Mining equipment must be able to withstand these extremes without degradation. Radiation. Beyond Earth's protective atmosphere and magnetic field, spacecraft and astronauts are exposed to relentless solar radiation and cosmic rays, which can damage electronics and pose severe health risks. Robust shielding is critical. Microgravity. The extremely low gravity of asteroids presents unique challenges. Traditional mining techniques that rely on gravity to hold equipment down or move materials will not work. Specialized anchoring systems and material handling methods are needed. Loose regolith could simply float away. Current technology, while rapidly advancing, is not yet fully capable of the scale required for space mining to be truly profitable. Autonomous robotics, human intervention in deep space is limited. Therefore, mining operations must be highly autonomous, capable of self-diagnosing problems, adapting to unforeseen conditions, and executing complex tasks without real-time human control. This requires significant advancements in AI, machine learning, and robotics. In space extraction and processing, developing machinery that can extract minerals from an asteroid's surface or interior in microgravity, in a vacuum, and then process and refine them, is incredibly complex. Traditional crushing, grinding, and smelting processes are designed for Earth's gravity and atmosphere. New techniques such as thermal extraction, chemical leaching, or electrostatic separation are being investigated. Transportation and return. Once resources are extracted, how do you get them back to Earth, or to a lunar base, or to an orbital fuel depot? This requires robust, cost-effective transportation systems. Safely and economically returning large quantities of material to Earth's surface is a major hurdle. Technologies like mass drivers, electromagnetic launchers, or asteroid redirection systems are theoretical but far from practical application for high-volume returns. Power systems. Deep space missions require reliable and powerful energy sources. While solar panels are effective closer to the sun, or for operations in shadow, more advanced power systems like compact nuclear fission reactors, kilopower, may be needed. Resource characterization. Developing highly accurate remote sensing and in situ instruments to precisely map an asteroid's composition before a mission begins is crucial for economic viability. Knowing exactly what you'll get before committing billions of dollars to a mission is paramount. 12. Economic viability. Even if the technical challenges are overcome, the economics of space mining remain uncertain. Upfront costs. The initial investment required for space mining missions is enormous, billions of dollars for research, development, launch vehicles, and spacecraft. Recouping this investment requires significant returns. Market disruption. If an M-type asteroid delivers trillions of dollars worth of platinum, it could flood Earth's market, causing platinum prices to plummet and potentially making the entire project unprofitable. This requires careful market analysis and strategies to control supply. Demand and applications. While demand for critical minerals is high, the true economic viability will depend on where these resources are used. If they are primarily for in-space manufacturing and propulsion, the economic model shifts significantly, becoming more about building a space economy than shipping material back to Earth. This is a critical distinction. This final frontier also brings complex legal and ethical questions. Ownership and property rights. Who owns the resources on an asteroid? The 1967 Outer Space Treaty states that no nation can appropriate outer space. However, it does not explicitly forbid private entities from extracting resources. New national laws are emerging, but international consensus is still needed to prevent potential conflicts. This is an evolving area of international law. Environmental concerns. Even though space is vast, there are still environmental considerations. What are the long-term impacts of large-scale asteroid mining on the space environment? Could it create hazardous debris fields? How do we prevent contamination if potentially life-bearing planetary environments are discovered, though unlikely on most target asteroids? Without clear international regulations, there is a risk of a gold rush mentality, where multiple entities rush to extract resources without coordinated oversight, potentially leading to chaos and unsustainable practices. Despite the immense challenges, the drive to mine space resources is powerful, built on a consensus that humanity's long-term prosperity and expansion depend on it. This journey will be incremental, characterized by both bold leaps and cautious, methodical steps, step by step, from water to metals. The first phase of space mining will likely focus on the most immediate, valuable, and accessible resource: water ice. Lunar water ice. Missions to the lunar poles have already demonstrated significant water ice reserves. This will be crucial for establishing lunar bases and serving as a testbed for ISRU technologies. Extracting, purifying, and breaking down water into hydrogen and oxygen on the Moon will be a monumental achievement, paving the way for asteroid-based fuel depots, NEA water. As technologies mature, missions will target the water content of C-type near-Earth asteroids. Establishing a network of orbital fuel depots, resupplied by asteroid-derived water, would revolutionize space travel, making missions to Mars and beyond far more feasible and economical. This would be a true game changer, breaking the tyranny of the rocket equation that dictates the amount of fuel needed to launch fuel. Once water extraction and utilization are proven on a commercial scale, the focus will gradually shift to metallic resources, high-value metals from NEAs. Initially, smaller quantities of high-value platinum group metals from S-type or M-type NEAs might be targeted. These could be returned to Earth for terrestrial markets or used for specialized manufacturing in orbit. The economics here are complex, but the high-value to mass ratio makes them attractive targets. Large-scale main belt mining. The grand vision of tapping into the truly immense wealth of the asteroid belt, like 16 Psyche, is a longer-term prospect, likely decades away. This would require an entirely new level of infrastructure, including large orbital processing facilities, advanced robotic fleets, and even human crewed operations in deep space. To fully realize the potential of space mining, continued breakthroughs in several key areas are essential. Advanced robotics and AI, truly autonomous, self-repairing, and self-optimizing robotic systems will be indispensable. Imagine swarms of intelligent mini-miners working in concert on an asteroid, adapting to changing conditions for months or years without human intervention. In space manufacturing and 3D printing, the ability to print complex structures and components using asteroid-derived metals will be revolutionary. This isn't just about extracting resources, but truly building entire spacecraft or habitats in space, dramatically reducing Earth launch costs. Imagine a fully self-sufficient space economy. Propulsion systems. More efficient and powerful propulsion systems are needed. Ion thrusters are a step forward, but systems like nuclear thermal propulsion or even more exotic designs, capable of both high thrust and high efficiency, will be crucial for the rapid transport of large quantities of material. In space energy generation, reliable, powerful, and scalable energy solutions for long-duration deep space operations are critical. This includes advanced solar panels, potentially solar concentrators for high-temperature processes, and compact fission power systems for distant or shadowed operations. Resource characterization, developing highly accurate remote sensing and in situ instruments to precisely map an asteroid's composition before a mission begins, is crucial for economic viability. Knowing exactly what you'll get before committing billions of dollars to a mission is paramount. Broader impacts: a transformative future. The successful development of space mining could have profound impacts, far beyond simply acquiring more resources. Multiplanetary economy. Space mining is a foundational pillar for establishing a truly multiplanetary civilization. It provides the necessary raw materials and fuel for sustained human presence on the Moon, Mars, and orbital habitats, lessening our reliance on Earth and opening up new frontiers for industry and settlement. Reduced Earth environmental strain. While not a complete solution, a vast supply of space resources could alleviate immense pressure on Earth's ecosystems from terrestrial mining, allowing for environmental restoration and more sustainable practices on our home planet. New industries and job creation. The space mining industry itself, from robotics and AI development to materials science and space logistics, will create entirely new economic sectors and generate countless high-tech job opportunities. Technological spin-offs. As with all grand challenges like space exploration, technologies developed for space mining are bound to have spin-off effects that improve life on Earth, such as advanced robotics for hazardous terrestrial environments, and new materials and energy solutions. Scientific discovery. Asteroid missions undertaken for mining purposes will also yield invaluable scientific data, enhancing our understanding of the early solar system, planetary formation, and even the origins of life itself. Every mission is also a scientific expedition. The vision of space mining is grand, challenging, and undeniably audacious. It is a testament to human ingenuity and our relentless drive to explore, innovate, and prosper. From the gleaming, metal-rich core of 16 Psyche to the icy veins of carbonaceous asteroids, our solar system holds resources that could reshape our future. The Platinum Planet isn't just a fantasy. It's a symbol of the immense wealth and potential that awaits us beyond our atmosphere. This race to unlock the cosmos' treasures has already begun, propelled by private companies, supported by national space agencies, and driven by humanity's fundamental needs and aspirations. The challenges are immense: the vastness of space, the harshness of the environment, the complexity of the engineering, and the uncharted waters of space law. But the rewards are even greater: a future abundant in resources, sustainable expansion into the cosmos, and the birth of entirely new industries. This isn't just about wealth. This is humanity's next great leap, an adventure poised to fundamentally transform our economy and even our place in the universe. Are you ready to witness humanity's greatest gold rush? A true rush to the stars? Wandering through the vast cosmic ocean, alone, with no sun to orbit and no star to call home. This is the life of the enigmatic voyagers of interstellar space, rogue planets. What secrets do these unbound worlds hold? And could they harbor life in the dark, cold expanse between galaxies? The birth of a rogue planet. Rogue planets don't just appear. Their existence is the result of dramatic events in the cosmos. 1. The gravitational slingshot, a planetary system's internal strife, in the early stages of a planetary system's formation. A protoplanetary disk of dust and gas gives rise to numerous protoplanets of varying sizes. The gravitational interactions between these young planets are highly unstable. Like a group of children running in a confined space, when a massive protoplanet comes into close proximity with a smaller one, its immense gravity acts like a slingshot, accelerating the smaller planet and flinging it out of its original orbit. If the force is great enough, the ejected planet achieves escape velocity, leaving its home forever to become a rogue planet. 2. The close stellar encounter. An invasion by a third party in dense star clusters. Stars are relatively close to each other. When a star with its own planetary system passes too close to another star, the gravitational forces between the two stars clash violently. This close encounter can disrupt the stable orbits of the planets. The powerful tidal forces, like a cosmic tug of war, can strip a planet from its parent star's gravitational grasp, giving it enough kinetic energy to break free and become an interstellar orphan. 3. Direct formation in nebulae. The born wanderers, unlike the first two scenarios, some astronomers propose that rogue planets can form directly within nebulae without ever being captured by a star. In the giant molecular clouds where stars are born, there are regions of lower density alongside the main star-forming areas. In some special cases, the dust and gas in these regions can also clump together under gravity, forming a planet-sized object, however, with no powerful gravitational center nearby to capture it. This newborn object is destined from the start to drift alone in the cosmos, a born wanderer. The astonishing number of rogue planets. Astronomers' estimates for the number of rogue planets far exceed our initial imagination. With the help of the latest observation technology and data analysis, we are gradually unveiling this massive rogue army hidden in the darkness. Initially, scientists predicted that the number of rogue planets could be very large through various models and theoretical deductions. More recently, with the deployment of new generation telescopes like the James Webb Space Telescope, JUICE, our ability to detect exoplanets and analyze data has made a significant leap. While the JUICE primarily observes distant stars and planetary systems, its profound insights into the formation and evolution of exoplanets provide a more precise basis for estimating the number of rogue planets. The prevailing scientific view is that there could be billions, or even trillions, of rogue planets in our Milky Way galaxy alone. This number might even far exceed the number of stars in the galaxy. This suggests that in the cosmos, rogue planets are the norm, while planets with a star's protection are the minority. How do we find these ghosts? Rogue planets have no starlight to reflect and emit almost no light of their own, making them incredibly difficult to observe with traditional telescopes. However, modern astronomers are gradually catching their traces through clever indirect detection methods. 1. Gravitational microlensing detection. This is currently one of the most effective methods for detecting rogue planets. According to Einstein's theory of general relativity, any object with mass warps the spacetime around it. When a rogue planet passes between us and a background star, its gravitational field acts like a giant alienus, bending and magnifying the light from the background star. This process is known as gravitational microlensing. Because rogue planets have relatively small masses, The microlensing events they cause are usually very short-lived, lasting only a few hours to a few days. To catch these rare, fleeting events, astronomers must continuously monitor the brightness of thousands of stars. A brief, characteristic brightening of a star's light could indicate that a rogue planet has passed in front of it. By analyzing the shape and duration of the light curve, scientists can even estimate the mass of the rogue planet. 2. Finding clues in JUICE data processing. The James Webb Space Telescope, with its unparalleled infrared observation capabilities, is bringing about a revolution in exoplanet detection. While the JUICE cannot see rogue planets directly, its powerful data processing and analysis capabilities are helping us detect them indirectly. For example, the JUICE can more accurately observe the processes in the early stages of a planetary system's formation, helping us better understand the mechanisms and probabilities of planets being ejected. Furthermore, scientists are using the JUICE for deep observations of nebulae and young star clusters, hoping to find those rogue planets that were ejected early in their formation. These young rogue planets may still retain some residual heat, emitting a faint glow in the infrared spectrum, and the JUICE is the perfect tool for capturing these weak signals. Unveiling the tip of the cosmic iceberg. The discovery of rogue planets is profoundly changing our understanding of planets and the universe. They are not just the orphans of the cosmos, but direct evidence of the processes of planet formation and evolution. Their sheer number forces us to re-examine the role of planets in the universe and raises new questions. Do these rogue planets have liquid water? Do they possess a thin atmosphere? Is it possible for life to survive in such a harsh environment? As detection technologies like gravitational microlensing continue to improve, and as new generation observational tools like the James Webb Space Telescope continue to operate, our exploration of rogue planets will enter a new phase. Perhaps in the near future, we will not only be able to accurately estimate their numbers but even get close to them, lifting the veil on these cosmic wanderers and gaining a more comprehensive understanding of the vast universe we inhabit.
Jupiter, the undisputed giant of our solar system, almost became a second sun. Its immense size and mass are extraordinary, yet they fall short of the threshold needed to ignite nuclear fusion. Instead of blazing like a star, Jupiter radiates a quiet, internal heat left over from its formation. But where does this constant internal heat come from? What drives the tumultuous storms and ceaseless winds that sculpt its magnificent atmosphere? Today, let's embark on a journey to uncover the mysteries hidden beneath Jupiter's dazzling clouds, exploring the powerful forces that have shaped this gas giant into a cosmic masterpiece. As you approach Jupiter, the planet reveals itself like a cracked mirror, its surface split into dazzling bands of clouds that stretch across its vast girth. Brown belts and pearl-white zones alternate, forming winding patterns around its equator. These stripes, far from being mere decorations, are the marks of immense atmospheric forces. Jupiter's atmosphere is divided into concentric bands by powerful east-west jet streams, which race at extraordinary speeds, shaping the planet's outermost layers into a dynamic system. In the brighter zones, ammonia clouds rise from the depths, reflecting sunlight with their white and pale gold hues. In the darker belts, we glimpse deeper atmospheric layers, where ammonium sulfide and other compounds dye the clouds in hues of rust red and amber. Each band flows in the opposite direction to its neighbor, as if colossal forces are locked in a perpetual tug-of-war, sculpting Jupiter's atmosphere into bold, distinct patterns. The winds that race through these bands are like nothing on Earth. Wind speeds can soar to hundreds of kilometers per hour, far exceeding the fastest hurricanes or jet streams on our home planet. High-altitude jets can even reach speeds of over 650 kilometers per hour, fueled by centripetal forces generated by Jupiter's rapid rotation. The result is a mesmerizing interplay of light and dark bands, where clouds churn and spiral, creating a seamless, flowing marble of color. But this isn't just a surface spectacle. Deep convection powered by Jupiter's internal heat drives everything. Hot gases rise from the depths, forming towering cloud bands, while cooler air descends, leaving behind clear skies that expose the planet's darker layers. This constant motion sustains the endless atmospheric dance that defines Jupiter's appearance. Amid this swirling chaos lies one of the solar system's most famous features, the Great Red Spot. This massive storm, an orange-red oval in Jupiter's southern hemisphere, has raged for centuries. The Great Red Spot is an anticyclonic system, a high-pressure vortex rotating counterclockwise. Its clouds are rolled tightly into a dense elliptical shape, towering above the surrounding layers. The storm's iconic red hue is still a mystery, though scientists suspect it may be caused by phosphorus-rich compounds or complex organic molecules drawn from the planet's depths. At the storm's edges, wind speeds can reach up to 430 kilometers per hour, twisting clouds into fantastical shapes and creating spirals of white ammonia clouds. First observed over 150 years ago, the Great Red Spot has been shrinking steadily, its diameter now roughly half of what it was at its peak. Even so, it remains the largest storm in the solar system, rotating once every 6 Earth days and towering tens of kilometers above the surrounding clouds. Occasionally, flashes of lightning illuminate the storm's depths, brief yet powerful bursts of energy that reveal the dynamic forces at play. The Great Red Spot, however, is just one of countless storms that dot Jupiter's surface. The planet's atmosphere is alive with turbulence, with small storms and vortices scattered across its vast expanse. Strings of white oval smaller anticyclonic systems similar to the Great Red Spot appear fleetingly. Some storms last for decades, while others dissipate in an instant, their fates determined by the ever-shifting winds. In 2000, 3 small white storms merged into a larger system named Oval BA, which later turned red and earned the nickname Little Red Spot. Fast-moving jets stretch and elongate these vortices, creating waves and ripples at the intersections of light and dark bands. In some regions, Kelvin-Helmholtz waves form, shaped by wind speeds moving at different rates, while dark, boat-shaped clouds drift silently through the jet streams. Bright clusters of clouds, akin to popcorn, mark areas of violent convection, where storms rise from the depths to pierce the upper atmosphere, without a solid surface to disrupt them. These storms can delve deep into Jupiter's atmosphere, living long and raging fiercely in ways Earth's storms never could. The poles of Jupiter offer a different, yet equally mesmerizing, spectacle. In the northern polar region, 8 massive cyclones form a near-perfect octagon around a central vortex. Each cyclone spans 1,500 to 2,800 kilometers in diameter, spinning independently yet bound together in a stable formation. Similar patterns are found at the southern pole, where 6 cyclones form a hexagonal array, rotating with precision and balance. These polar storm clusters have remained stable for years, suggesting the presence of intricate physical mechanisms, perhaps involving fluid dynamics or the influence of polar jet streams. Occasionally, lightning flashes across the polar regions, briefly illuminating the cloud tops with silvery light. Jupiter's lightning storms are far more intense than anything on Earth, occurring at both high altitudes and deep within its atmosphere. High-altitude lightning is a particularly fascinating phenomenon, occurring in frigid layers where temperatures plummet to -88 degrees Celsius. Here, ammonia acts as a natural antifreeze, allowing water to remain in a liquid state despite the extreme cold. During violent storms, hailstones are flung into these upper layers, where they melt and mix with ammonia, forming a slurry that generates electrical charges. The result is shallow lightning, brief, eerie bursts of blue and gold that light up the upper atmosphere. Deeper in Jupiter's atmosphere, traditional thunderstorms occur, where water exists in solid, liquid, and gaseous states, mirroring the complex dynamics of Earth's thunderclouds. These storms produce intense lightning strikes, each far more powerful than those on Earth. The Juno spacecraft has detected tens of thousands of such strikes, along with the piercing radio signals they emit, which resonate across Jupiter's immense magnetic field. Above Jupiter's atmosphere lies another breathtaking phenomenon, its auroras. These dazzling displays of light are among the brightest in the solar system, burning with an intensity hundreds of times greater than Earth's auroras. Unlike the brief auroras caused by solar storms on Earth, Jupiter's auroras are nearly constant, fueled by both solar winds and the planet's massive magnetic field. This magnetic field, 16 to 54 times stronger than Earth's, captures high-energy particles and directs them toward the poles. When these particles collide with Jupiter's upper atmosphere, hydrogen molecules become excited, emitting ultraviolet and infrared light. The result is a brilliant display of auroral rings that soar and dance over the poles. Jupiter's moons also play a role in this spectacle, particularly volcanic Io, which ejects sulfur and oxygen into space. These charged particles are swept into Jupiter's magnetic field, igniting auroras near the poles and leaving glowing footprints. Europa and Ganymede also contribute to this light show, their interactions with Jupiter's magnetic field creating additional auroral patterns. Even Jupiter's faint rings add to its mystique, though they are barely visible compared to Saturn's, discovered in 1979. These delicate rings are formed by dust particles, generated by impacts on small moons like Amalthea and Adrastea. The particles are tiny, most only micron-sized, and they're faint. Ghostly presence is best seen in infrared or backlit conditions. Jupiter is not merely a planet, it's a dynamic system, a symphony of swirling clouds, fiery storms, glowing auroras, and faint rings. Its immense magnetic field, internal heat, and countless moons form a cosmic orchestra of unparalleled grandeur. As we gaze at Jupiter, we see more than a planet. We witness a timeless narrative of transformation, energy, and beauty. A giant still writing the unfinished chapters of the universe in the depths of the starry sea.